Sure. So Robert Zimmerman is a postdoc here at Imperial College. He just arrived a month and a half ago from the University of Toronto. You can see on his affiliation, he lists them both because he did this work while he was there. He worked with Anita and Vinay and I on this project over about a year, mostly while he was remote. He came and visited us at Imperial for about 3 months, I guess, 2020.
Technically 2 in person.
2 months in person. Early 2023 was it?
April and May.
April and May 2023 where we met. And we made good progress on this project very quickly in those 2 months and kind of finished it up over the year that followed. So I guess that's a big enough, long-winded enough introduction.
Yeah. Okay. All right. Well, thank you, David, and thank you, Vinay, for inviting me to talk here. So yeah, I'm talking about our project that we worked on over the past year or so, and this is about using hidden Markov models to model light curves from X-ray sources.
So if I may interrupt, Robert, quickly.
Yes.
The question that we had just before you joined, I was telling people about how we started looking at copulas, and the question was, why didn't that work? So do you have any comments on why we switched from copulas to hidden Markov modeling?
Well, the two are not mutually exclusive by any means.
Sure.
So in fact, in the paper, we leave using copulas for the state-dependent distributions as future work. But for now, we just, in interest, I guess, for model simplicity and parsimony, just to start with assuming conditional independence, which is something that a lot of HMM people use. And yeah, it's possible that copulas can do a better job. Although there are known issues for copulas with discrete margins, because in that case, they're known not to be unique. And there are sometimes problems with parameter estimation, but it can, in principle, be done. So that's something to look into for future work.
Excellent. Thank you.
Okay. So good to go with the presentation then?
Indeed.
Okay. All right. So on this slide, I'm sure everyone in the room knows more about this than me, but so certain stars produce these flares, short duration flares, which emanate from their coronae. And what we're interested in doing is understanding the long run proportion of time that a star spends in either a flaring state or a quiescent state. And also from a statistical perspective, it's just interesting to understand the data generating process, what process actually kind of generates the observed data. So for a star like the sun, that's very close, and it's close enough that we have continuous information in continuous time, but also like flux measurements, and you can do what Stanislavski et al. Did, which is to fit a hidden Markov model where the observed data is continuous, and in some respects, that's somewhat easy. But for the stars that we have, these stars that emit X-rays, all we really have are these light curves, which are computed from lists of photons recorded by our X-ray telescopes, which are just time and energy of each photon. And our case study is this star, EV-LAC. This is not my photo. This is from NASA. So this is, from what I understand, this is a youngish, quite feisty star, something like 15 million light years away. And it's known to produce a number of flares or have produced a number of flares in the data. And this is what our data looks like. So from those lists of photons, we construct these light curves. So essentially, we bin those photons together into, in our case, we take windows of 50 seconds. We count how many photons hit the detector within each 50-second interval. That's how we discretize time. And also, in this case, our data is bivariate. So we split the data into both hard and soft bands. The hard bands, we look at all those photons which are in the 1.5 to 8 kiloelectron volt range, and the soft band, which is the 0.3 to 1.5 range passband. So this is what the bivariate data looks like. You can see in figure 2 here. And these are from 2 different epochs of measurement. The first one is from September 2001, and the other one is from March 2009. And I think each one comprised about an Earth day and a half or so of measurements. So understanding flare state emissions it's been studied before, but most of the literature kind of uses ad hoc type rules or things like machine learning methods, black box models, or black box methods such as neural networks to kind of understand the data. And for the EV lab data that we have here, the best guess for the proportion of time spent flaring in September 2001 is 39% and 29% for the March 2009 epoch. And that's based on this paper by Mortar, I'm sure I'm pronouncing that wrong, et al., 2010. So this is the data that we're working with here. And what we do in this project is we use hidden Markov models in order to model the states of flaring and quiescence. And more specifically, we take a two-stage approach in what we do. So in the first stage, we use hidden Markov models to predict the values of some continuous process taking place inside the star. And that process, in some sense, induces the observations that we see in those light curves. And I'll explain what I mean by that more specifically on the next slide. And in stage two, we use a finite mixture model, which is actually itself a special case of a hidden Markov model, in order to approximate the distribution states, and that's what we actually use in the end to estimate those proportions of time spent in flaring and quiescence. So what is a hidden Markov model? At least in discrete time, which is what we deal with in this project, a discrete time hidden Markov model consists of an unobserved Markov chain, which we denote using x's. So xt minus 2, xt minus 1, and so on, really x1 to x big T. And these all take values in some state space, which we just call script x over here. And we have an observed time series, y1 up to yt, and we write those as vectors because in this case, our observed data is bivariate. And how it works is that it's the underlying Markov chain, which we cannot observe, and each value of the Markov chain induces the distribution of the corresponding observation at that particular time. So at time t, xt is generated, so to speak, and that induces the distribution of yt. I see we have a hand up.
Yeah, so I hate to interrupt, but I just want to clarify one point about the last bullet, conditional independence. Do I understand that correctly to mean that in a given state, for example, let's take the flaring state, that the data in that let's say some time interval over which the system is in the flaring state for some, let's say, long interval of time, that the data in that interval is modeled as uncorrelated, that there's no variability structure modeled in that interval. Is that correct? Is that what this last bullet means?
That is correct. That is correct. That's exactly what the conditional independence assumption for hidden Markov model says. That's exactly right. Yeah. Once you know the states, then the distribution of your observations are indeed conditionally dependent on that information.
Got it. So, but isn't that doesn't that mean then that you can't deal with any of the shape, like the shape of the flares, or any variability during the so-called flaring state is simply ignored by this model? Is that correct?
So it's a great question, and I'm going to get to that in either the next slide or the slide after, because probably in your head you're thinking of the state space as being just flaring versus quiescent. And in fact, that's not what we do. That's what we tried, but it didn't work. So I'll show you that.
Okay. Sorry. Okay.
Okay, thanks. Yeah, so if the kind of basic HMM setup is clear, I'll go on to the next slide. So let's talk about discrete state HMMs first, and that is the case when the state space is finite or technically countable, but that's very, very rare. Most of the time, the state space is finite for a discrete space HMM, and we could label the state, say, from 1 up to k. And these just represent labels, so that could very well be flaring, quiescent, flaring 1, flaring 2, quiescent, and so on. So this is a discrete space HMM, and such a model is characterized by 3 ingredients. So the first one is the probability that the first observation, the first state, say x1, that's just the distribution for that particular x1. There's nothing that comes before it, so it's just its own kind of marginal distribution. That's we denote that by delta I. In other words, that's the probability that x1 is in state I. Then we have these transition probabilities, which usually show up as a matrix, but that's not exactly necessary. So this is gamma ij, and that's simply the probability that we go from state I at time t to state j at time t plus 1. And it's an assumption of this HMM time homogeneity that this will not depend on t. In other words, it doesn't matter what time it is, the probability that you go into state j, given that you're in state I right now, will always be the same. That's given by this gamma ij. And the last thing are these state-dependent densities or mass functions. So given that we're in state I, this gives basically the probability of our observation, seeing our observation. And if we're working with discrete observations, such as, we are right here, this is a genuine mass function. So this really is the probability of observing our data at time t, given that we're in state I, and lambda I is just a state-specific parameter. Okay, sorry. And with that in mind, the likelihood is given by this expression over here, which looks like a lot, but actually it's quite straightforward if you kind of break it down. So observe the x's, which means that we have to sum overall, but we're marginalizing overall. So in the end, this is literally the probability that we observe the data that we have, right? We're summing over all possible states that could have generated that data. So here we have the probability that we were in state 1, summing over all possible state 1s, then the probability that we observe the data in state 1, and then we kind of push forward with the other observations through there. Memorize this exactly, but kind of keep in mind the structure of this likelihood because it'll come back later. And something that's very important to note is that even though the number of terms in this sum is exponential in k, it turns out that you can actually evaluate this likelihood efficiently using these classical tools from HMM theory, in particular. Sorry. Using these tools from HMM theory, in particular, there's the Ford algorithm, which evaluates this in O of k squared instead of exponential in k, which is very, very useful. So we can evaluate this likelihood efficiently. So the question, as we were just talking about with Jeff's question, why not assume a 2-state or maybe a 3-state HMM for our data? Well, it's exactly as we said, because once we try and fit such an HMM and then we look at the classifications from that resulting fit, we see that that conditional independence assumption is quite obviously violated, right? So if we look at figure 4 up here, on the left, we fit a 2-state HMM, I guess intuitively thinking that one state would be flaring and the other state would be quiescent. And although the flaring state was kind of, it colored these peaks, if we look at the points within each kind of colored peak, these are supposed to be conditionally independent, but clearly they're not, right? There's this very obvious temporal trend. And similar if we did a 3-state HMM, same kind of thing, right? You look at the set of data that's colored, and if the process did the classification correctly, then each set of individually colored points should be independent, and they're obviously not, especially in the areas that are assumed to be, very clearly flaring, right? So that tells us that the discrete state HMM, at least with a small number of states, is actually not quite appropriate. So we need something a bit different here. So now let me introduce continuous space HMMs. And if you understood the discrete space HMM, this is really not a big leap. All we do is replace that discrete space hidden Markov, that discrete space Markov chain that we can observe with a continuous space one. So that underlying chain, x1 to xt, takes values in a continuum. And for simplicity, we assume that that continuum is r to the d for some d. And when the dynamics of this Markov chain are specified, the resulting model is an example of a state space model. And for a very typical and very relevant example, here's a Poisson state space model. And here's what happens. So if we have xt, which is a vector now, so d equals 2 here, xt takes values in the plane, and we'll say that xt is xt1 and xt2, it's a vector. So Conditional on knowing xt1 and xt2, we can say that the observed values, the yt's, which are also bivariate, so yt1, yt2, is going to be given by a product of Poissons. And when I say product, I mean that the components of y are conditionally independent. So y conditional on knowing what xt is, yt1 follows this Poisson distribution, and yt2 follows that distribution, this Poisson distribution over here. So that describes the observed data conditional on the underlying chain. And as for the dynamics of the underlying chain itself, well, this is a standard vector autoregressive process of order 1, vector autoregressive process. So here, each xt is a linear function of the previous xt minus 1. So linear here is just the matrix with some parameters. And then there's some noise, or if you're a time series person, you might call this innovations. But the epsilon t's, these noise terms, they are independent of each other, and they're mean 0, and they have their own covariance structure like so. So this is more or less the most general Poisson state space model you can get, assuming that your xt is bivariate. And we consider 3 such models, and all of them are nested within each other, going from simplest to more complicated. So the first one, we take d to be 1. So here, the underlying continuous chain xt is just a single kind of scalar valued process. And you can see the kind of specification here. So now xt, this is just a standard AR1 process that you might have seen in time series. In model 2, we kind of upgrade that. So now xt is back to being a vector with 2 components, like so. So this is the same thing that we saw in the previous slide. The only thing is that the distribution of the xt's, the distribution of the errors more particularly, is given by this limiting distribution, or the distribution implied by this limit here, as the correlation between the 2 components of x goes to 1. And when that limit is attained, then what we have is that xt1 and xt2 are actually linear functions of each other. So that's actually quite convenient to work with. And then finally, model 3, we have an uncorrelated vector autoregressive process. And that's like before, but we don't assume that the correlation parameter goes to 1. Instead, it's just some value between -1 and 1, and that's given by this model down here. Okay. So just like with the discrete space HMM, the continuous space version of that is fully specified by similar kinds of ingredients. It's just that the discrete versions from before are replaced by continuous analogs. So before we had an initial distribution for x1, now we have an initial density. Similarly, before we had those transition probabilities from going from one state to another, and now those are replaced by this transition kernel, which is basically just a density in each argument. And finally, the state-dependent densities are the exact same thing. So conditional on being inside state little x, this is the probability of observing the data whenever. Okay, and the likelihood function for this general state space model is given by something very similar to what we saw before, except now we have a continuous analog. So instead of summing over every possible state sequence, now we're integrating over every possible state sequence because we're integrating over this these continuous spaces script x. And there's a problem now. There's no forward algorithm for this. This cannot be computed, let alone maximized. So by kind of upgrading to this more general model, or this continuous model, we run into some serious computational problems. Fortunately, there's a way to deal with that. There's a very clever way that was discovered, or at least published in around 2011 or so. And essentially what we do is we approximate that continuous space HMM with a discrete space HMM, just with a lot of states. And here's how we do it. Normally x is, R or R2 or something, so that's an infinite unbounded state space. But if we can reduce it to a bounded subset of R to the D, large but still bounded, and then we partition that subset into a bunch of hyperrectangles, say a union from I equals 1 to m of AI. And within each component of that union, we choose a point inside it, let's say the center of it, just for convenience. Then we can actually approximate that continuous space likelihood by this. So we still have the same probability of being inside. So now you can think of a discrete state as being the state of being inside one of these AIs. So now we have M states in quotes where the ith state is the event that we are inside AI. So that's what we get. And if we change the notation, tweak things a tiny little bit, what we get is this approximation. And you might recall that this is exactly the form of the discrete space HMM likelihood from before. And you'll recall that we can evaluate this efficiently, or we can compute it efficiently using the forward algorithm and all those nice HMM tools. So that's what we do. We use these approximations to approximate those continuous space HMM likelihoods, and then we run some model selection. So we maximize the approximate likelihood numerically, and for standard errors, we use the parametric bootstrap. And we use the LRT, or at least we try to use the LRT for model comparison, because these models are nested within each other. So in principle, the LRT works. The LRT for choosing between model 1 and model 2, the LRT works very easily, and we reject the null hypothesis that that model 1 suffices with very, very strongly, p-value very, very small. But for model 2 versus model 3, the LRT actually fails. The reason, first of all, the LRT statistic to compute is actually quite difficult, because mainly that parameter rho, which shows up in model 3, which you'll recall takes values between -1 and 1, is estimated at this 0.9999987, which you'll notice is very close to 1. And it turns out that when you're doing the LRT and your parameters lie on the boundary of your parameter space, things kind of get messy and the asymptotics are no longer valid. So you can't really do the LRT. So we go with other stuff, kind of more heuristic checks, and in the end, we do select model 2. So model 2 was
Robert,
the one. Yes, sorry.
about the discretization that you had, that you were describing. So how many bins do you think that are at minimum necessary for this thing to work and maintain?
So that's a good question. And there's a book by Zucchini et al. From 2016 or so, and that's on hidden Markov models. And they have a chapter on this exact kind of approximation. And they use several real world examples, and they compare the exact value of the likelihood with the approximated value, and they compare the AICs that you get from both. And they find that once you get to about a partition of size 40, then things kind of even out, and there's not much difference between the two. So a discretization of around 40 bins seems to be sufficient in most cases, assuming you're using a Gaussian model for the underlying state space.
So does that depend both on the size of the data as well as what might be in the data? So for example, if you have long flares, that might be different from if you have a large number of small flares.
Yeah, I mean, in theory, if the model is correct and the more data you have, then the higher the chances are that the state process kind of drifts outside your proposed, what they call the essential domain, that A that we're taking as the approximation of the entire state space. But you can do kind of post hoc checks, which is what we do in order to check that. So you use this model and you predict those underlying states, and you see how far they stray into kind of the edge of your essential domain. And if it looks like you're getting too close to the edge and your essential domain A is not big enough, then you can go back and expand it.
And just for the record, how many spaces, I mean, how many bins did you choose?
We used 40. 40.
Okay. Right. Thank you.
Okay. So going on, so we went with model 2. Would you recall for that particular model, it is a bivariate xt, but one component is a linear function of the other. And for convenience, we can specify everything in terms of, say, the first one. So now we switch to scalar xt's. And so now the question is, how do we perform inference on those hidden states? Well, what we can do is local decoding, and that is essentially the posterior state predictions for each state given the observed data. In other words, we're able to calculate the probability of being in any particular state, say xt, given the observed data, and there's an algorithm for computing this for discrete space HMMs. And then we simply take the state xt, which maximizes this probability. And just to be clear, the probability, the parameter for this probability, sorry, that should be an eta, not a theta, or eta hat. This is the fitted vector of parameters that we would have fit using numerical methods for that likelihood. So what do we do with these state predictions? What we do, in principle, these predicted states have their own distribution, which, at least in theory, but it's completely intractable. I don't know if anyone's ever actually written it down. It's not easy. But what we can do is we can approximate it with a mixture model. This is a two-component finite mixture. So we assume that these posterior state predictions all arise from some mixture of two distributions, say F1 and F2. This is a standard way of writing a two-component mixture model. Alpha is the mixing parameter, and that's between 0 and 1. And if we assume that F2 is the distribution that corresponds to the flaring state, then 1 minus alpha is exactly the overall proportion of time spent in the flaring state. So now we're on to stage 2 of the analysis. And we can do this in two ways. So if we're lucky enough to have a clear sustained period of quiescence at hand, which we can hopefully ascertain just by looking at the light curves, say that's from T1 up to TQ, then we can use those predicted states from T1 to TQ as training data, and we can train a kernel density estimate for that quiescent component of the mixture model. And we do this by approximating that mixture component, that component of the mixture model using a step function. And what we're able to do is come up with a custom designed EM algorithm to fit both components. And you can see the results over here in figure 5. So here, if you look at the left component, I'm looking at just the fitted density of these xt1s. And the second component is that that one's a step function, and then the one on the left, which is partially trained on the period of quiescence, is a KDE. And then you can fit the resulting mixture, which gives you the curve on the right over here. And we can actually just read off the estimated parameter of that alpha hat, and that tells us that in this case, and this is for the September 2001 epoch, by the way, that gives us an estimated time spent in flaring state of about 45%. On the other hand, if we're dealing with the March 2009 data, where we don't particularly have a very obvious sustained period of quiescence, then what we found is that it's actually better to use a three-component mixture model. And in this case, all the components are normal distributions. And in this case, the left in quotes, the left two components correspond to quiescence. And to elaborate on what I mean by left, you see that all these normal distributions have mu's, mu1, mu2, and mu3. Those are the means of the normal distributions. So it's, and these are scalars. So it literally is the two smaller of the mu's that we assign to the quiescent state. And it's mu3 and the third component, which we assign to the flaring state. And finite mixture models, finite mixtures of Gaussians are a classical application of the EM algorithm. So that's very easy to fit as well. And we do so, and you can see the results in figure 6. So on the left, we have the individual component mixture densities, F1, F2, and F3 multiplied by their fitted mixture components. And then on the right, we have their sum, which is the total mixture distribution in the end. And we get, if we multiply the estimate of alpha 3, that's the proportion of time spent in state 3, which we assume to be the flaring state, we get about 27%. And the numbers that we get actually are quite similar to those earlier ones from the 2011 paper. So that's good. We're kind of in agreement there. And just to give a kind of real world interpretation, this is a plot that Vinay created. So Vinay, please correct me if I completely bungled this explanation here. But here we're looking at the spectra from both epochs kind of overlaid with each other. And we're looking at the spectra in the quiescent intervals and the flaring intervals. And what you can see is that for the flaring interval, the overall brightness is higher and the continuum is stronger and more prominent during the flaring state. So we do have a different thermal signature here. So that's what we've done, and there's certainly potential future work to do. So I'll list kind of three kind of categories of potential future work. To begin with, we can consider more complex models for the state-dependent distributions. So these are the distributions of the observed data given the state. So that's like these state-dependent Poisson distributions that we have. So as we talked about before, we currently assume conditional independence, that the two energy bands are conditionally independent, but that might not be the case. And we can relax that assumption by using state-dependent copulas. As I mentioned, there are some caveats when you use discrete marginals for copulas, but it's still doable, and that would be interesting to see. Moreover, there are other temporal patterns in the data that we can study. So, for example, instead of both flares appearing at the same time, we can have a flare in one band, which precedes a flare in another band, and so on. And these temporal patterns can be generalized considerably. We can also look at the state process itself, the conditional state process. So right now we have a standard vector autoregressive process, and that assumes that these conditional distributions are multivariate Gaussian. But you can relax that assumption. You can swap that with, say, multivariate T distributions if you want heavier tails, or even mixture distributions for more complicated physical mechanisms. Then it becomes a bit harder to fit, but in theory, it's still doable. And finally, right now in this project, we've used bivariate data. So we use 2 passbands, but we can just as easily split the data into more passbands. And if we want to do that, if we want each passband to have its own kind of state process, then we would move the corresponding state process itself, that x1 to t, into a higher dimensional state space. If we do that, there's many more covariant structures available than in just 2 dimensions, and there's a lot to choose from. There's a problem, though. If we have a higher dimensional state process, then even the efficient estimation technique that we use, that discrete space approximation of the continuous space HMM, that will suffer severely from the curse of dimensionality. And it's unclear at this point if there's a way to get around it. So that's also left for future work. And that's all I have. So thank you very much.
Thank you, Robert. That's nicely done. Any questions? Jeff has one. But Jeff, but just before you ask your question, I just want to point out that there's a bunch of stars people here. So Robert, if you could go to that spectral image for a moment, I just want to make one point to them.
Sure.
That one of the main results that popped out of this was that if you look at the upper panels, that's telling you what the quiescent emission is. So the different spectra over different wavelengths. So these are grading data from obtained with the wait, I forgot whether HETG or LETG, but the important point is that we just took the with no additional analysis of any sort, we just took the intervals over which the quiescent part was set to be set and overplotted the spectra, and you can see how nicely it matches. So it's also supported by full spectral analysis that you get similar temperatures and normalizations for the quiescent state, and these are data that are separated by nearly 8 years, and the quiescent state remains exactly as it was, and it was it's very well determined. which came as a bit of a surprise to me, even though it shouldn't have, because there have been several studies which have sort of identified a persistent quiescent state even in active stars. So anyway, so this is the kind of thing that stars people look for. So just want to make that point.
Vinny, can I ask, there are 2 points in from this figure. One is that the quiescent state looks different than the flaring state.
Mhm.
And the which you were emphasizing that I didn't quite pick up on before, was that the flaring state and the quiescent states are the same in the 2 epochs.
Not the flaring state, because it's difficult to see in this thing, but there is more variability that you can see in the flaring state. So each flare is its own unique snowflake, but the quiescent state in both cases seems to be very similar to each other.
So how do you see the difference in variability?
Yeah, not necessarily in this plot, but if you remember, we had this plot with the hardness ratios, which showed a much larger scatter for the flares, whereas the quiescent part was almost exactly in the same part of the grid.
That plot clearly showed, although there were big errors, just because flaring the individual flares are much shorter than the quiescent state, so there's less data, so that it's error. But those flares were all over the place. But the 2 epochs, when you average over the flares, they do look quite similar, don't they?
If you look at the full, in a sense, yes, because there is only so much that a spectrum can do. You got the spikes that you see over there are emission lines from particular ions, and they're always going to show up at the same place. So what you should probably look at here are the differences in the shades. So for example, the bluish versus the greenish parts, which tell you which has more emission in a particular line at in one epoch compared to the other. But again, you get similar yields in this thing because once you have a flare, you have a higher temperature, and it's difficult to see obvious differences without actually modeling the spectrum, which we can't do because there are too few counts in several of the flares. So that's why we had to look at the hardness ratios.
And last question, do you know why there's negative values in the lower right panel?
Because this is the difference between the two. So not the difference. The lower panel is the one where the quiescent part has been subtracted out.
Oh, just actually subtracted out.
Yeah,
I see.
Literally subtracted out. Yeah. So what is left? What you see in the lower panel is the flaring component, excluding what's in the upper panel. Okay, sorry, Jeff. Go ahead.
No, not at all. Yeah, this is really great stuff. And it gets to a common problem in stellar astrophysics and lots of other areas where you have light curves where it looks like there are flares. You see flares and you see what look like quiescent intervals maybe between the flares. The question I've always wrestled with is that really true? Are you seeing discrete flares, or is there really a continuous process that something?
Yeah, so actually, Jeff, so that is exactly the reason we all get so excited, right? Because normally we wouldn't be able to tell whether the quiescent part is really a quiescent component or whether there is a bunch of flaring going on. Exactly. But this is telling us that it is really, there is a different heating mechanism operating, that if the quiescent part is so stable across a decade, it cannot be because of flaring.
Yeah, exactly. So, and I've even had a hard time phrasing my question in a objective way that can be really made into a well-defined problem. And I think your method does that so nicely, in the sense that if you look at the continuous state space distribution, or I realize there are problems with curses of dimensionality and so on, but I wonder if there isn't another problem connected with overlap of flares, and maybe that's something you've thought about. But if you look at the light curves, you often see some isolated flares, but you also see some cases where it looks like there are several flares together in time and extended in time, so they overlap. And of course, in the limit of many overlapping flares, you go to Gaussian noise, where things are completely different. So it's kind of a vague question, but have you thought about the impact of flare overlap on the attempt to separate discrete states out of the data?
So maybe I should let Robert answer this, but Robert, if you can go to the plot with the light curves, especially the one with the second one, I think has an example of a overlapping. Yeah, there you go. The one on the right clearly shows an overlap, right, where before the first flare that begins as the observation begins, before it finishes decaying, there's another flare that's on it, clearly, yes. Right? So yeah, so that's this method itself doesn't make the distinction that you're talking about, where you could find a very large number of flares that are possibly, that could mimic something like a quiescent state, but this post-HMM spectral analysis that is telling us that the quiescent state is different from the flaring state. Yeah.
Right. Okay.
And I don't know if Robert has any other comments on this.
No, I think you explained it very well. So yeah, I mean, it kind of goes back to the problem of assuming, a finite state HMM, right? You can maybe have different, maybe two states for flaring, right? But inherently, just in the HMM structure, there is no overlap. And, we recognize that as a deficiency quite early on. So by switching over to the continuous space formulation, right, we're no longer, it's not that the underlying state space, the underlying Markov chain is, flaring, quiescent, or whatever, but rather it's this continuous process inside the star. And, how that determines flaring versus quiescent is left for the stage 2 analysis, but really modeling the observed data, what we're doing here, worrying about like overlaps and flares in the data is no longer a problem.
And I should probably also mention that there is another work by Esquivel et al. That uses an HMM, a discrete space HMM, to actually pick out parts of a flare. So they use 3 states. I think I think something like quiescent, onset, and decay, or something like that.
Could you go to the slide where you show the model, the 2 equations, yes, exactly. So, well, let's see. Yeah, I guess these are called, the first one is called sometimes the observation equation, and the second one is the state space equation. It strikes me that this issue of overlap would be covered by altering the first equation and explicitly allowing for a given state, allowing the so-called flare to extend beyond the time at the beginning and ending time of that state. But I don't know, that I'm just rambling there. But I realize there's another question, and I don't want to take too long, but I'm puzzled by the second equation, the autoregressive thing there, X is essentially a label, isn't it? It's X says whether you're in the flaring state or in the quiescent state. But this relation is a numerical relation. Is this really an autoregressive model for the parameters of the flaring? Like if you have represent the flaring and quiescent states with parameters, that it's really the parameters that X contains and not just a label as to which state you're in?
No. So when we move to the continuous space, the values of the state process are no longer labels. Like you can't think of this as, like flaring quiescent or flaring 1, flaring 2. These are purely like real numbers, or rather like actual vectors. So they live in R2 or RD in general. So, we're thinking some continuous process inside the star that that emits, so to speak, vector valued data. So it's no longer categorical.
I see, but in the category, so for, let's say, just a two-state categorical system, there'd be a different formalism here. It wouldn't be an autoregressive equation of this form. It would be different, right? It would be transition probabilities.
Exactly. So there is a very fundamental difference between the discrete space and the continuous space. Exactly. Like in the discrete space, yes, of course, they're just labels, and there's an equation like this equality is meaningless. That's right. The labels are fully determined by that transition matrix. Exactly.
Okay, one last detail that bothers me in the epsilon term is, let's call it the innovation. Having its mean be 0 is a little problematic to the extent that it represents shocks, new information coming in, explosive input in the astrophysical source. It's typically not a zero mean process at all. It's a positive only thing. So can you really represent that sort of situation with a zero mean stochastic innovation of that sort?
Well, the flare has to go away too, right? I mean, the flare goes up, but it also comes down.
Well, that's the response of the innovation. I think in astrophysics as a series of delta functions of different amplitudes. In the extreme case where you have a flare is just ignited by one instantaneous event, and then it decays according to the autoregressive.
It's also in the exponential, Jeff. So it's in the Poisson part, at least, it comes out as positive definite. Would that help?
Well, yeah. I mean, I think this is an issue of X and Y here, because what you see is a delta function convolved with a shape in Y, but that's a little different from X. Anyway, I'm sort of going off on a tangent, but just quickly, if you didn't have zero mean epsilon there, would that cause severe problems in your analysis, or could you incorporate a mean value?
I don't think it would cause a problem, really. I mean, it would just be, this kind of mean thing. So every time you have a new observation, then it kind of like drifts forward in general. So yeah, as for the physical plausibility, I'm not sure.
But the way it is now, X is a random walk. If you made epsilon have mean 1, that X Markov chain would go off to infinity, right? The longer you watch the thing, the more positive X would become on average.
I don't think that's true for the if the autoregressive process is what is it, convergent, or I forget what the terminology is, but I know that's an intuitive picture that, but I don't think it's true. I think you can have a positive, innovation without a runaway.
Okay, if you make the 0 1, that means that you're simply, what that simply means is you're going to add 1 at every t. You can still subtract off the mean. You could say epsilon t mean 1 is the same as 1 plus what he has there. So you essentially you just add t to that bottom equation and you get mean. That's the same thing as making the epsilon half mean 1. So it would become xt equals phi xt minus 1 plus t plus epsilon written just the way it is now, or just write plus mu times t for any other mu.
Yeah, I know what you're saying. I'll
Maybe, maybe we should let Stephen ask this question.
I'm sorry, I just remember having an argument with a guy about 10 years ago on that same issue, and I think I won the argument, but that's beside the point. I know what you're saying, but a moving average representation can have a positive innovation without running away. I'm pretty sure that's
Okay, we can probably discuss that
sorry.
over time. But Steve has been patiently waiting. Maybe I should give him a chance to.
Could we move to the spectra again?
Sure.
Steve, we can't
There
hear
you
you clearly.
Oh, can you hear me better now?
Very faintly.
Sorry.
You're quite clear for us, Stephen. Maybe Vinny,
Okay.
Vinny needs to turn up his volume.
Okay, well, I'm kind of yelling out here, but sorry. Looking at the quiescent, it looks like the levels of the emission lines are changing significantly from one time to another. But I guess the question is are they kind of changing like all in tandem with each other? In other words, is the temperature staying the same? And you're just scaling by amount or something? For
the quiescent part?
Yes.
Yeah, the temperatures are almost identical. I mean, I think it was like 1.2. Oh, I don't remember the numbers now. It's either 1.25 versus 1.26 or 1.35 versus 1.36, that sort of thing.
Okay, but then the total flux might be a little higher in one than the other. In other words, you have more of something at the same temperature.
The temperature, the normalization was almost the same too. Sorry, the one other thing to note here is that these are the raw spectra. Sorry, yes, this is ACCHTG. These are the raw spectra, and the effective area did change because of contamination over the decade.
Oh, okay, so that might account for the changes in the emission line strengths. Okay.
Yeah, especially at the soft end, you'll see more 1885 than 10679.
Well, is this it's kind of interesting because in some sense you would almost expect maybe that as the star rotates, as it moves through its magnetic cycle, that you might actually have a change in the temperature of the quiescent might stay the same, but maybe the change in the amount might change.
Yes,
as you
but
get more
it did
or less.
not.
Sorry?
Yeah, yes, but it did not.
Okay, that's
interesting. That is the the dog that did not bark in the night.
Okay, and then I presume that the flare temperatures and overall flux levels were quite a bit different.
Yeah, they did. Yeah, that they do.
Fine, that's basically my question.
Yeah. Okay, thank you. Phil?
Yeah, thanks. Really interesting talk. I had, I guess, 3 parts to this, actually. They should be quick, hopefully, though. The first is, it looks like you took out the rotation signal from this whole thing. So was that just a detrending you performed first? The second question is related to performance. So if you had like a month of data for a different star, like how long would it take to be able to actually get the flaring time out of that? And then the third one is, so you modeled these distributions. Would it be possible to pull out things like the integrated flare energy or like a flare frequency from that in addition to the total time spent flaring over the time period.
Okay, for the first question about the rotations, I'm not sure what you mean. That's probably because I don't know enough about the data, so maybe I should let Vinay answer that.
Yeah, we didn't do anything. So these being Chandra X-ray data, we don't see much in the way of rotational signal.
Oh, right.
In
Okay.
this. So yeah, I suspect that what you're thinking of for tests like those.
Yeah, exactly.
Yeah, so yeah, we see nothing like that in X-rays. So there's no way we could model that. I forgot the second question.
I remember the second question, and that I can definitely answer. So you asked what happens if we have like a month of data or so. So that goes back to the time complexity of the forward algorithm to evaluate that approximate likelihood. And if you have K states and T observations, so I guess you take a month and divide it into 50-second intervals, and there would be your T. So it's big O of T times K squared. So basically for a fixed K, that's a fixed, fixed number, a fixed partition size of that essential domain, then the cost of approximate the likelihood will scale linearly with T, which is very helpful. So
Right.
basically it can be done.
Yeah, so just in plain English, it scales with, as long as you don't change the model, just scales with the length of the light curve.
Yeah.
So that's not too bad.
Yeah. And then the third question, you were asking about extracting certain parameters. Could you remind me?
Yeah, like looking at the total flaring energy, like integrated under the, I guess, distributions for those flaring times or similar statistics from that.
Yeah, I can answer that partially. We did think of trying to do that. We didn't do that for two reasons. One is that Dave Hunemarder and others in their paper actually went and looked at modeled each individual detectable flare. So, they have that sort of information already done. And the second thing was this method it doesn't, I mean, we knew that we couldn't separate overlapping flares. So we didn't try to, anything that we tried to do there would suffer from incompleteness and contamination. So we didn't do that.
Right. Okay, thank you.
Yeah, sure. Steve has another question.
Yeah, this is maybe just my not understanding the details of the technique. But when you were originally describing it, it sounded like the epsilon was almost a noise term. But then when Jeff was talking about it, it sounded more like it was an evolutionary term where new things could be added or subtracted or something. So what actually is it?
Yeah, so I mean, this goes back to like time series and really your interpretation. So time series people call these terms innovations because at each time T they provide new information. It's not just plain simple noise because each epsilon T determines that XT. But if you kind of like fix a single T, then you can sort of think of it as noise because you know that the current, I shouldn't say observation, the current state is given by this kind of deterministic function of the previous state, this deterministic linear function, phi times the previous state, and then plus this epsilon t, which is zero mean. So you could kind of consider it noise. So it's more of a matter of interpretation than anything else.
So if epsilon were just, if the variance were zero, right? So if epsilon were just zero, x would go to zero. The phi's are such that x is that true?
So that depends on the initial distribution of x1. If x1 has like a non-degenerate distribution.
Well, for fixed x1, if the phi1 and 2 are equal to 0 and phi1 and phi2, phi1, 2
Mhm.
is equal to 0. It's a diagonal matrix, and phi1 and phi2 are less than 1.
Then it will go to 0 for
It goes
sure.
to 0. But aren't there constraints on the phis because it's a what do you call it, a stationary process?
Yeah. For this one, the constraints are actually kind of complicated. What we considered the most complex one was model 3 over here, which took the off diagonals to be 0.
Yeah.
And in this case, the constraints were indeed that phi1 and phi2 in absolute value are bounded above by 1. That's right.
Right, so that means that the X, it's only the innovations that keep in that way, it's kind of like what Jeff was saying, that the innovations, you get they're what push X back up.
Right.
And, so if you get a flare, because if you look where the X ends up in the equation above, you get a positive innovation. It makes the X get bigger, and that's the flare. So I mean, those epsilons are kind of important actually for the overall model.
Right. Yeah. And that's why it's fair to call them innovations. That's why
yeah.
they call them time series. Yeah.
I mean, they're fit to the data, it's like they kind of, when the data goes up, that's when the epsilons go up, right? So
Yeah, like if you fixed a single xt and you kind of view this as kind of regressing on xt minus 1, then I guess it's sort of fair to consider it noise. But as far as the process itself, as a time series, no, the epsilon t's do certainly provide more information.
I'm getting a little confused, I think, but isn't it fair to say that you're really trying to incorporate the randomness of the transition probabilities from one state to the next? That's the inherent nature of a Markov process. I think if you just wrote that equation without an epsilon and interpreted it as the transition probabilities are what introduces the randomness in the update, to me that's maybe equivalent to what you're talking about, but a better way to think of what's happening in the discrete and the finite state space problem. Is that a fair statement?
this is when you say without the epsilon, you mean just setting epsilon equal to 0 essentially.
No, not introducing it. I don't understand the meaning of it in the context of a Markov process. A Markov process says that the transition from one state to the next is governed by a transition probability matrix in general. If you have a multiple state, a multivariate state, and it's not adding a random process, it is playing in the random process implicit in the transition probabilities.
Right, but if epsilon weren't there would be nothing random in the way it's written here.
Not explicitly, but implicitly. What I'm trying to say, when you go to find out what x of n plus 1 is, numerically, you would play in the probability distribution represented by the transition probabilities. You wouldn't add something to x because x is, as we were saying before, x is a categorical variable, and adding a number to it is meaningless. I don't know, maybe I'm just looking at it from the wrong point of view, but to me, the essence of a Markov process has nothing to do with adding noise. It's transitioning from one state to the next according to a given distribution.
In this case, I don't believe X is categorical, Jeff, because it's supposed to be continuous.
Well, right. I was everything I was saying was for the finite case. Finite state space where it is categorical with many categories maybe, but still. I mean, I'm doing a similar problem with genetic sequences, and you don't, when you're looking at A, C, G, and T, you don't add some random number to go from one to the next. You play in a distribution, and it seems to me in any finite state space, it doesn't make sense to add a random term to the update equation for states. But
well, this is all for a continuous case. I mean, do you have the equation somewhere?
Right.
The equation, I mean, it's not an equation, it's just the transition matrix, right?
Do you have it written down somewhere?
Just a gamma ij. I don't say anything more than that.
Where?
Here, transition probabilities.
I see, yeah, so in the discrete case, you have these gamma ij's, I guess if it's just two states, there's four of them, you stay in the quiescent state, they probably go from quiescent to flaring, they probably go from flaring to quiescent, probably you stay in flaring, right, so there's four numbers that sum to one.
Right, yeah, exactly. Well, they sum the columns.
Oh, yeah. They sum to two. Yeah.
Yeah, maybe something just to clarify. So this continuous process, the AR1 process, that is a perfectly legitimate Markov process, right? It's the transitions are not described by a transition matrix, but it is a completely valid discrete time Markov chain where, you know, in a Markov chain, the Markov property says that the distribution of xt is determined by xt minus 1. And that's exactly the case here, right?
It's a different kind of Markov.
It's a different kind of Markov process than we typically see with, well, obviously with finite state spaces, but it is a totally legitimate Markov chain.
Yes, I completely agree. And not to muddy the waters, but have you ever looked at higher order Markov, higher order AR models? Does that help at all?
So we kind of left that to future work. We mentioned that in the paper, but importantly, if you have a higher order Markov chain, you can induce that to a standard first order Markov chain just by playing around with it a little bit. So
Right.
it increases the computational complexity, but you can still model it all as a first order Markov chain in the end. Yep.
Okay, well, I've got to go, but thanks very much. This is a fascinating talk. Ideas. I hope you pursue this. So.
Thank you for the questions.
All right. Any other questions?
We have a question from the room here. Yes, go ahead.
Have you ever considered using like the frequency domain and periodograms, looking at periodograms of the data rather than the time domain?
We have it. We didn't do that.
No.
Could you repeat the question?
All right, go ahead.
Yeah. Have the speaker have ever considered the frequency domain rather than the time domain of the data, like the periodogram?
Oh, no, we did not. Because I mean, I guess because the flares are not don't appear periodically, so we didn't even think of trying to do anything with that. At least I didn't.
What else? Once.
Okay. All right. So if there are no more questions, thank you again, Robert. This was very interesting. And we got a talk next week by Herman, who's presenting a problem about extragalactic neutrinos. And we'll see you all next week, same time.
Good.
Thank you.
Thank you.
Bye, everyone.
So is it a particular AR that you